In this video, we're going to review the different models of the atom and in particular talk about the Bohr model of the atom and then electronic structure, meaning how electrons are actually arranged within an atom. So just as a summary of what we talked about in the previous video, with Dalton's atomic theory, he had these 5 ideas about it, and we learned that 1 and 2 are actually not entirely true, but 3, 4, and 5 hold up. So he thought that an element is composed of tiny, indivisible, indestructible particles called atoms, but we now know that due to nuclear chemistry and nuclear physics experiments, we actually can break up atoms into smaller pieces. So that's kind of what's happening when we're crashing atoms into each other, and then also when you have nuclear fission, we're actually breaking up atoms. Number 2, all atoms of an element are identical. So that's not true because we know of a thing called isotopes. An isotope is when the number of neutrons is different. So for example, we have carbon-12 versus carbon-14. Both of them have 6 protons. However, carbon-12 has 6 neutrons and carbon-14 has 8 neutrons. They're both still carbon, because they both have 6 protons in the nucleus. That's what defines them as carbon. But because they have a different number of neutrons, we call them isotopes. So again, 1 and 2 are not entirely true today, but 3, 4, and 5, atoms of different elements combine to form compounds. That's true. We could have water or ammonia or methane. Atoms of different elements combine to form compounds. So water, ammonia, NH3, methane, just as examples. Number 4, compounds contain atoms in small whole number ratios. That's true. We can't have half of an oxygen atom in a water molecule. You either have 1 oxygen or 2 oxygens or 3 oxygens. And then atoms can combine in more than one ratio to form different compounds. So for example, with hydrogen and oxygen, we could have an OH that happens to have a minus charge overall. That's called hydroxide. We could have H2O, which is called water. We could have H2O2 called hydrogen peroxide. So it's not always the same combination. We can mix it up for sure. Next was J.J. Thomson's model. So knowing that we had positive and negative particles, he theorized that we had what's called like the plum pudding or raisin pudding model, where you've got like a pudding of positive charge and then the electrons as negative particles within that soup or within that pudding. And this was his idea. He proposed that basically the electrons were evenly distributed throughout a homogeneous sphere. But then we learned that that wasn't entirely true when Rutherford did his gold foil experiment. So as a result of his gold foil experiment, he concluded that there must have been an extremely small, dense nucleus where the rest of it is mostly empty space, and that's where the electrons were. And he figured out that the size ratio between the two, so the nucleus itself was significantly smaller than the atom. So to put it in perspective, here's an analogy. There's plenty of analogies out there. If the atom was the size of the Superdome, the nucleus would be the size of the marble. There's plenty more. But the point is that the nucleus itself is extremely tiny, and we've got a difference in magnitude. So these two numbers here, that's a difference in magnitude of 10 to the 5th. So 10,000 or 100,000 times smaller. Now, what's new for this week? Oh, actually, one more thing on Rutherford. So this is very important. So this table 4.1, is very important for you to make sure you understand and memorize. But he concluded that there must be neutral particles in addition, so inside the nucleus. And then it was Chadwick that actually discovered the neutrons later. It's about the same size as a proton, but it doesn't have any charge. So our symbols, we'll use E negative if we want to just represent a single electron. Protons are positive and neutrons are neutral, which is why we have a little 0 and a plus sign and negative respectively for those two. Protons and neutrons are inside the nucleus, so they're basically together, they compose the nucleus, and electrons orbit the nucleus. So that's why when we draw our atoms, we'll have the electrons going around. And the detail for the electrons going around we're going to discuss in this video right now. The charge, so it's very important to remember that electrons are negative, protons are positive, and of course neutrons are neutral. When we talk about forming charged particles called ions, it's going to be important to remember that electrons are negative. And then in terms of their mass, protons and neutrons are pretty much the same size. There actually is a very, very slight difference, but for day-to-day chemistry, looking at the periodic table, it's perfectly fine to just remember that they're about the same size. Meanwhile, electrons are incredibly tiny compared to the proton and the neutron. So if we wanted to try to figure out the mass of the atom, we're pretty much not even going to worry about the mass of the electrons because they're so incredibly tiny in comparison. Now, the new model of the atom for this week is the Bohr model of the atom. So he speculated that the electrons orbit around the nucleus in fixed energy levels. So we call that pretty much being quantized, and we're going to go into detail in next week on what we mean by quantized. But the point is the electrons are only found in specific levels and nowhere else. So we've got, for example, these three orbits. Here's our nucleus, tiny, tiny nucleus at the center. And what the Bohr model of the atom is basically suggesting is you can have electrons here, this far from the nucleus, and this far, but you are not going to find electrons this close to the nucleus, or this close. You might find more further out, but in terms of in between these two levels, you're only going to find them here or here, not somewhere in the middle. Now, what we mean by energy levels, and also we'll introduce this, what we mean by sublevels as well, but we've got many, many levels. So we've got, here's a level 1, and then these two together comprise level 2, and these comprise level 3, and then each one has sublevels, and they're kind of like stair steps, which is getting back to the quantized thing, which again, we'll get into more detail. We'll talk about the wave nature of light next week and what that means for electrons and atoms. Now, this first level, so what they've called 1s right here, that's the first energy level, and it has just one sublevel, and we call it 1s. The second energy level, it has two sublevels, which we call 2s and 2p. And then the third energy level has three sublevels, and we call them 3s, 3p, and 3d. And there's fourth level, 5 level, 6 level, and so on. So then the fourth energy level will have 4 sublevels, and we will call them 4s, 4p, 4d, and then after d, it's 4f. And in theory, the fifth energy level has 5 sublevels, but then that fifth one is never, ever used. So we actually haven't given it a name. I think they may have given it a theoretical name, but it's effectively never used because we never get that high on the periodic table in terms of needing a place to put electrons. Now, the maximum number of electrons in each sublevel depends on what the sublevel is. So we have these designations S, P, D, and F. And the S can only hold 2, P can hold 6, D can hold 10, and F can hold 14. And these numbers may seem random, but there actually is a pattern. So S is kind of like the first one, and then P, if you go by odd numbers, 3, 5, and 7, and then 1 times 2 is 2, 3 times 2 is 6, 5 times 2 is 10, and 7 times 2 is 14. And that's where those numbers come from. And then Y times 2, we'll get to that in a minute because apparently it's not on this slide, but each little, well, it is on the next slide, so I'll just show you that, but it can hold 2 electrons, and here there's 3 little spots on the P sublevel, and each one can hold 2, and that's how we get to 6. But the maximum number of electrons per level is basically obtained by adding the maximum number of electrons in each sublevel. So what we mean by that, so let's take level 3, for example. Level 3, we just said it has an S, a P, and a D. So 3S, 3P, and 3D. So the 3S Any S sublevel can hold 2, any P sublevel can hold 6, and then D sublevels can hold 10. So the maximum number, we're just going to add those together. That means we can have 18 electrons total on level 3. Another example, level 1. Level 1 just has the one S. S sublevels can only hold 2, so it's just 2 electrons total can fit on that first level. So going back to this diagram, I can't change colors. My apologies. Okay, so on this one, so this level can hold 2 electrons, this can hold 2, and this can hold 6 to make 8 total, and this can hold 2, 6, and 10 to make 18 total. So on the second sublevel, we can fit a total of, no, I'm sorry, on the second level, we can fit a total of 8 electrons, 2 on the S sublevel and 6 on the P sublevel. Now, by sublevels, another way to think of sublevels is orbitals. So this is where the electrons actually are. So we were just talking about levels, but then, what exactly is in that 2p sublevel that makes it special that it can hold 6? Well, electrons live in what we call orbitals. An orbital is a region of space where there is a high probability of finding, and this should say, an electron. An orbital is a region of space where there is a high probability of finding an electron. It's not a guarantee, and it's traditionally about 90% probability of finding the electron. So here's an example of what the 1s orbital or 1s sublevel looks like. You can think of S for spherical. That's not what it actually stands for, but just to help you remember. In the quantum mechanical atom, orbitals are arranged according to their size and shape. So that S, these are spherical. And then this is, if you were to put them all together, the P has another shape and D has another shape, and we'll see those in just a minute. But all S orbitals, regardless of which level they're on, have a spherical shape. The higher the energy of an orbital, meaning like level 2 or level 3 or level 4, the larger its size. So that's why this 1s orbital is smaller than the 3s. And then going back to this drawing, that kind of makes sense. The 1s, if you think about distance from the dotted line to the nucleus, that's a certain amount of distance. And then if you compare the same thing going all the way out here, that's a larger distance. So higher energy levels will be physically larger in space as the higher you go. And higher the energy means like level 2 or level 3. So level 3 is higher in energy than level 1. So that's the S. Next is the P. P is an interesting shape. Sometimes we call them these dumbbell shapes. But there are 3 different P sublevels, and what they mean is simply the X, Y, and Z. So X, Y, and Z direction. And if you put them all together, it kind of makes this flower shape. So we've got this one, it says 2px because they're illustrating the P or AP orbital on the second level. And it's on the second level because, recall, level 1 just had a 1s. There was no 1p. So there's no such thing as a 1p sublevel. It doesn't exist. So we've jumped up to level 2. But you have one dumbbell shape kind of in the X direction horizontally. You've got another in a direction that is perpendicular. So perpendicular kind of meaning got like a 90-degree angle between them. And then in the third dimension, you've got another dumbbell shape in the Z. And this just happens to be their shape. We're not saying that this is an orbital and this is an orbital. That is their shape. Their shape is this double lobe dumbbell shape thing. And in each one, you can fit 2 electrons, which is how we got up to 6. So we said, going back, we said the P sublevel holds a maximum of 6 electrons. That's where that comes from. Because we have 3 different P orbitals in the 3 dimensions, X, Y, and Z, and each one holds 2 electrons, coming up with 6 total. And then lastly, we're going to look at the shapes of the d orbitals. The f orbitals are certainly very interesting, but you don't have to worry about them for the fundamental chemistry course. If you're curious, go ahead and Google them. But the d orbitals kind of have these flower shapes or clover leaf shapes, and we have 5 this time. So recall that we said on the third level, we have 3s, 3p, and 3d, and all s sublevels have 2 electrons, p's had 6, and d's could hold 10. Well, this is where the 10 comes from, because we've got 5 different orbital shapes, essentially, and each one can hold 2. So there's 5 different d's, and they haven't given their names here. They've got interesting names, but you don't have to worry about that. But 4 of them have this nice, pretty cloverleaf shape, and one of them is kind of like a dumbbell with a donut. But this is where that 10 comes from, and you'll find that these get used most often with the metals that are in the middle of the periodic table. So just a quick little sketch of our periodic table. This section in the middle, this is where the d orbitals get used to house electrons.